Hello and welcome to this lecture on advanced electric drives. In the last lecture, we are discussing about the field structure with a permanent magnet, the field structure of a permanent magnet DC motor. The field is usually stationary. In a DC motor, as we know, the field is stationary, and for a permanent magnet DC motor, the field is permanent magnet. So, we have seen various classes of magnets like alnico magnets, ferrite magnets, samarium cobalt or rare earth magnets, and also niobidium iron boron magnets. So, we were just discussing the field structure with permanent magnets. Let us first see the field structure with ferrite alnico magnets. This is the field structure with alnico magnets, and as we know that we need very thin and long alnico magnets. Now, these are the magnets that is placed in the field. Okay. It's also the magnet, and this magnets are thin and long. You can see here we have a north pole and we have a south pole here, and this is the pole shoe to facilitate the flow of the flux. Similarly, we can have this for a two pole structure. We have one north pole here and one south pole here ultimately. So, this is basically for a two pole structure. Now, if we see for a four pole structure, the structure will be like this with alnico magnets. Alnico magnets are thin and long magnets. So, this is one magnet, 2, 3 and 4, and these 4 magnets in total result in 4 poles, 2 north poles and 2 south poles. This is the north pole which is produced by these 2 north poles, and here we have the south pole which is produced here, and then we again have a north pole here, and again we have a south pole here. So, this is basically an example of alnico magnets which will result in 4 pole structure. Now, we can see another configuration also, like we have magnets which are arranged like this, and this is the north pole and this is south pole structure. We have the yoke, the pole shoe, and this is the rotor core, and this is a 2 pole structure. Now, similarly, we can also think of a 4 pole structure corresponding to this, where we have 4 thin and long magnets. Now, if we go to ferrite magnets, we have already seen that for ferrite magnets we need thin magnets, but with large width. We have this L by A ratio, Li by Ai, and for ferrite we need small l and large area, cross sectional area. So, Li is the length of the magnet and Ai is the cross sectional area of the magnet. Now, we see here that this is the arrangement with the ferrite magnet. This is Li, the length is small and the width is considerably large. This is basically the width of the magnet, Wi, and hence we will have a large cross sectional area. So, we have a thin magnet with large cross sectional area, which is the requirement of ferrite magnet. And this is for a 2 pole structure. We see here that this structure is resulting into ultimately one north pole here, and then a south pole here. We have the yoke, and the yoke is usually made up of soft iron to facilitate the flow of the flux. Similarly, we can also think of a 4 pole structure. The most expensive magnets are the samarium cobalt or rare earth magnets, because they have large Br and large Sc. We have already seen in the last lecture that if we see this rare earth magnet, so we are talking about the field structure. So, field structure with rare earth magnet. So, we have large the residual flux and also large coercive force. So, these magnets are expensive magnets and they are used for those applications where we need very compact motor. Because of large BR and large SC, essentially what we have large energy stored, because energy stored per unit volume is half into BH. We also know that energy stored per unit volume is equal to half B into H. So, this will be resulting in a BH product curve like this, and it is sufficient to have a very thin magnet yet have a considerable amount of flux density. So, essentially the ferrite core, the samarium cobalt magnets or rare earth magnets, they are very thin magnets, and with thin magnets also we can produce large flux density. So, we will see an example of the field structure with samarium cobalt magnet. So, this is the field structure we have with the samarium cobalt magnet. We are drawing a 4-pole structure. This is the rotor. We have the stator inner surface, and the magnets are placed here. This is one magnet, this is the other magnet, this is the third magnet, and this is the fourth magnet. So, we can have these four magnets here, and the polarities of the magnet can be suitably arranged. So, for example, this could be a north pole, this could be a south pole. So, this is a magnet. Similarly, this is a magnet, and we can have a north pole here and a south pole here. Again, we have a magnet here. We have a south pole here, and then we have a north pole here. We have another magnet in this case. It's a thin magnet, north pole and south pole. As a result, here we have 4 poles here. We have 4 magnets which will result into 4 poles, 2 north poles and 2 south poles. We can see the flux lines. The flux lines will be like this, that here is a magnet. So, we have north pole, flux lines will be coming out of the north pole and entering the south pole. So, this is the flux lines coming out of the north pole and entering the south pole like this. Then we can have another flux line which is coming out of this magnet. So, this is another flux line and entering here. For this, we can have the flux lines north pole and then south pole. Similarly, we have the flux lines here, north poles and south pole. Here also we have the flux lines, and this is the north pole and this is the south pole. So, ultimately we have here 2 south poles and 2 north poles. So, this is a south pole. So, we have a south pole which is created here, and this is also a south pole because the flux is entering. So, we have a south pole here, and here we have a north pole because the flux is going out. Here also we have a north pole. So, fluxes will be going out of this north pole like this, and fluxes will be entering a south pole like this. Here also we have south pole, flux will be entering, and we have north pole here, flux will be going out. So, we have seen an example of the field structure of a DC motor having samarium cobalt. Now, in this case, since the samarium cobalt magnet is having large energy density, we can have very thin magnets, and hence the structure or the size of the motor can be made very compact without compromising with the power. So, we can have very high power to weight ratio, the weight and volume can be reduced and the power can be increased by having samarium cobalt. The application of such kind of motors is for space application, where we have constraint of space, constraint of weight. So, we cannot have a very heavy material there, we cannot have a motor which is heavy. So, for space application, for aerospace application, we go for motors, permanent magnet motors having samarium cobalt magnets. So, with this we have seen actually the field structure of a permanent magnet DC motor. The DC motors, the conventional DC motors as we understand, has an armature and a field winding, and the armature has commutators and brushes, and we have friction contact with the commutator and brushes, and hence we are sparking at the brushes. We can also have motors without any brush, and those motors are called brushless DC motors. So, we will see the structure of permanent magnet motors which are used for brushless DC motor and permanent magnet synchronous motors. So, our next discussion is basically on brushless DC motors. So, this is abbreviated as BLDCM, and permanent magnet synchronous motor. And this is abbreviated as PMSM. Now, we can classify these motors based on the structure of the rotor. Now, both this brushless DC motor and permanent magnet synchronous motor work on the principle of synchronous machine. In the synchronous machine, we know the speed of the rotor is synchronous speed. The rotor will not run at any other speed than the synchronous speed. So, the principle of brushless DC motor and PMSM motors are essentially the principle of synchronous motor. So, based on the rotor construction, we can divide these motors. So, we will see the various classification of this motor based on rotor construction. So, we can classify this motor as number 1 is the rotor construction. Based on the construction of rotor, we can classify this motor is surface mounted magnet. Surface mounted magnet, and number 2 is interior magnet. As we know that in a synchronous machine, the field winding is usually the rotor. The rotor is the field winding, the stator carries the armature winding. Now, the field winding is not the conventional wound field winding. The field winding is replaced by permanent magnet. It could be 4 pole, it could be 2 pole, it could be 6 pole. Ultimately, the field winding or the rotor is a permanent magnet. Now, based on the housing of the permanent magnet, we can say whether the rotor is a surface mounted magnet rotor or an interior magnet rotor. Surface mounted means the magnet is mounted on the surface of the rotor, and again the surface mounted motor is classified into 2 categories. We can have the projecting type magnet or projecting magnet type, and inset magnet type. Let us see the structure of surface mounted rotor. So, we have the rotor here, and then in the rotor what we have done, it is a 4-pole structure. The magnets are mounted on the surface. Like this. So, these are basically the magnets. And the stator is around this rotor. So, we have the stator structure like this. So, this is a projecting magnet type motor. So, we are talking about the surface mounted magnet. So, here let us say we have a north pole here and a south pole here. So, ultimately we have the north pole which is seeing the stator, and we have a south pole here, and again we have north pole and we have south pole, and the rotors are fixed to the the magnets are fixed to the rotor using epoxy glue. Now, this is very easy to construct. We can have a rotor. The rotor is basically a soft iron core. This is the rotor core which is soft iron core, and the magnets are glued to the rotor using epoxy glue. Now, this construction is quite simple, but the motor is not robust, because the magnets are glued to the rotor using epoxy glue. So, you can't have a very high speed. If you have a very high speed, there will be high centrifugal force, the magnets may fly off. Of course, this is used for very low speed application where we can afford to have such kind of construction. This is one type of construction here. The advantage of this type of construction is this, that the air gap is uniform. We can see that the rotor and the stator is having uniform air gap. So, this is for projecting magnet type. And the characteristic of this is uniform air gap, and the magnets are held using epoxy glue. Magnets are held using epoxy glue, not very robust. Now, if we want to go for a little robot construction, what we do there is that the magnets are buried or pressed inside the rotor, and that is called inset permanent magnet structure. So, you will see an inset permanent magnet structure where we have the rotor here, and we can construct a 4-pole structure where we have the magnets are put inside the rotor like this. They are not projecting, they are inside the rotor, and this is why this motor is called inset type surface mount motor. So, this is the magnet, these are the permanent magnets which are inside the rotor, this is the rotor core, and the stator structure is here. This is the stator structure which is around the rotor, and similarly we can have a north pole here, south pole here, north pole and south pole. The magnets are arranged in such a fashion that we have 2 north poles and 2 south poles. Now, here the magnets are inside the surface of the rotor and they are held by means of a torque tube, so that they should not fly off. And this kind of construction is more robust than projecting magnet type, and this construction is called inset magnet type. Inset magnet type. Now, we will see the example of some very typical low cost brushless DC motor where the rotor construction is inset magnet type, where the magnets are placed on the rotor and they are held so that they should not fly off. Now, here the advantage is that more robust compared to projecting magnet type. This is the stator core, and the stator and the rotor are made up of soft iron. They are laminated structure, and inset magnet type rotor or permanent magnet brushless DC motors are preferred for many applications. Now, these are surface mounted type permanent magnet motors. Now, we can have another class of motors in which the magnet is buried inside the rotor, and those class of motors are called interior permanent magnet motors. So, we will see some example of interior permanent magnet motors. So, we have the rotor here, and we are again talking about a 4-pole structure, an equivalent 4-pole structure. So, we have the magnets which is buried inside the rotor. We can see here the magnets are not on the surface, but they are inside the rotor. So, these are the magnets. And we have some air gap which is created here, so that the flux will not short circuit in the rotor. So, this is north pole, and we have a south pole here. Again we have a north pole and again a south pole. We have the stator structure. So, this is the stator, and this one is the rotor. And this class of motors, which are interior permanent magnet motors, are very robust. They are used for high performance application. The speed can be very high because the magnets are well inside the rotor. There is no question of having centrifugal force, and the magnets will fly off, as we have seen in case of a projecting magnet type rotor. So, the magnets are covered within the rotor, and hence the rotor structure is very, very robust. This kind of motors are preferred for automobile application and for traction applications. So, with this, let us move forward to a basic structure of a brushless DC motor. We will see the operation of a brushless DC motor. Okay. Basic brushless DC motor. Now, in a basic brushless DC motor, we have 3 phases in the stator, and the rotor is a permanent magnet rotor. So, what we have in this case, we have 3 phases in the stator, and the phases are connected to 3 transistors like this. So, these are the 3 phases of the stator. We have the transistors here, and these are the 3 windings in the stator, and there is antiparallel diode here which will free wheel the inductive current, and this is connected to a DC source. This is VD. So, when the transistor is turned on, one of the phases is energized. We can call these phases as A, B, C or W1, W2 and W3. We have 3 different phases, and how are they arranged? They are arranged in the following way. This is the structure we have. We have the rotor, and the phases are arranged in the following fashion. One winding is here, other winding is 120 degree away from this, and the third winding is again 120 away from the other winding. So, this is how the windings are arranged. So, what we are seeing here, we have got 3 different windings, and 3 windings represent 3 phases of the motor. One phase is W1, the other phase is W2, and the third phase is W3, and they are phase shifted in space by 120 degree. So, we can call this to be W1, this to be W2 and this to be W3, and they are connected to this transistor, and the transistor is T1, this transistor is T2 and this transistor is T3. Now, what about the rotor? The rotor is having a 2-pole structure. So, for example, we can consider the rotor to be a magnet, and the magnet is having just 2 poles in the following fashion. So, in the rotor we have a magnet, and the magnet is having 2 poles, one north pole and other is south pole. All right, and in this case also what we have here, we have 3 optical encoders. We have an optical encoders, and we have 3 photo sensors, and we have 3 light sources. So, these are basically the photo transistor PT, and we have here PT1, PT2 and PT3, and this is arranged in the following fashion. We have an optical encoder which is realized like this. So, this hashed region is basically the shorter or the opaque region, and the region which is clean, that region is the transparent region. So, we have 3 photo transistor, and on the other side we have the photo source. So, whenever the opaque region is encountered, the photo transistor does not give any signal, or the signal is 0, and when the transparent region is encountered, the light passes, and the photo transistor, the corresponding photo transistor will give a high signal or a 1 signal. So, as the rotor rotates, the 3 photo transistor will give us the signals. Sometimes the photo transistor will be giving us high signal, and sometimes the photo transistor will be giving us a low signal. Now, let us assume that whenever a winding is excited, how do we excite a winding? We can excite the winding W1 by turning on T1. Similarly, we can excite the winding W2 by turning on T2. We can excite the winding W3 by turning on T3. We have 3 different windings, and the corresponding transistors has to be turned on to excite the winding. Whenever a winding is excited, a current is passed through it, and when a current is passed through that particular winding, the winding produces a south pole, and hence at the moment, let us say we excite W1. So, if we excite W1, what we have here is the following: a south pole is created here. Now, when a south pole is created here, this north pole is attracted towards the south pole, the rotor will rotate in the anti-clockwise direction like this, and when this rotates, this will be aligned along W1 after some time. The north pole of the rotor will be aligned along W1, and then PT1 will be covered. The phototransistor 1 will be covered. The opaque region will come and the phototransistor 1 will be covered, and hence we will have PT2 will be lighted. So, we have structure like this for clockwise rotation, anti-clockwise rotation. For anti-clockwise rotation, we give the following signals. What we do here, the phototransistor 1, PT1 feeds the transistor 1, and PT2 feeds the transistor 2, and PT3 feeds the transistor 3. Now, we see here that if PT1 feeds transistor 1, W1 is excited, and when the W1 is excited, a south pole is created and it attracts the north pole of the rotor. Rotor rotates in the anti-clockwise direction. Now, after some time, PT1 will be covered and PT2 will be lighted, and hence the pulse will be applied to W2, and then after some time PT3 will be lighted, and hence what we see here, the rotor will continuously rotate in the anti-clockwise direction. So, there has to be a position encoder like the present case. We have 3 phototransistors and we have a opaque disc, partly opaque and partly transparent, and in this case we make this 120 degree. This is 120 plus 120. So, that makes 240, and this is 120. So, when we make this disc, 240 will be opaque and 120 will be transparent. So, this disc will be pressed onto the rotor. So, it is glued on the magnet. The rotor is basically a magnet having a south pole and a north pole. So, what we do, we make this disc which is having 240 opaque region and 120 transparent region, and we glue this to the rotor so that this also rotates along with the rotor. So, this disc, this opaque and the transparent disc is glued to the rotor and it is rotating along with the rotor. So, as the rotor rotates, the disc also rotates. So, as a result, sometimes PT1 will be high, PT2 will be high after some time, and PT3 will be high. So, in fact, if we try to see the signal in this case, the signal will change in the following fashion. Say PT1, PT2 and PT3. How do the signals change? Initially we had 1 0 0. At this present situation, PT1 is lighted. So, we have 1 for PT1, PT2 and PT3 are 0 0. Similarly, after some time PT1 will be covered and PT2 will be lighted. So, 0 1 0. Then after some time PT1 and PT2 will be covered and PT3 will be 1. So, 0 0 1. And then after that the sequence will repeat, it will be again 1 0 0. So, essentially as the disc rotates, the phototransistors will be giving a signal, and one of the phototransistor will be on, and therefore one of the windings will be excited. And when one of the windings is excited, the attraction force is produced, the rotor is attracted toward the stator magnetic field, and when the rotor reaches that magnetic field, the magnetic field shifts to the other phase. So, continuously there is a rotation because the magnetic field shifts from phase W1 to phase W2 to phase W3. In fact, when we excite W1, we have a north pole south pole produced here. So, we have the field structure like this, the south pole is produced like this, and then after some time W2 is excited. So, we have the field which is produced is along W2. Similarly, after some time field 3 is W3 is excited, so the field is along W3. So we have a continuous rotation of this field. The field moves from W1 to W2 to W3 and the rotor follows this particular field. And this is the principle of brushless DC motor, a very simple brushless DC motor. Now, if we want to change the direction of rotation, we can also change the direction of rotation. So, we will see that for clockwise rotation, we can just change the connection. Earlier what we said, that output of PT1 should be fed to transistor 1. Similarly, output of PT2 will be fed to transistor 2 and output of PT3 will be fed to transistor 3. Now, here we will make a little difference. The difference is this: output of PT1 is fed to transistor 3 and output of PT2 will be fed to transistor 1 and output of PT3 will be fed to transistor 2. So, we are just seeing the operation of a simple brushless DC motor. We have 3 windings in this case and we were discussing the clockwise rotation. In the clockwise rotation, the phototransistor will be connected like this, that PT1 will be connected to T3. So, it means in the present condition we have this is PT1, PT2 and PT3. So, this is the phototransistor 1 and this is the phototransistor 2 and this one is phototransistor 3. So, when PT1 feeds T3 or W3 here, correspondingly the winding 3 is excited. So, we will have a south pole here. So, when we have a south pole in this case, this north pole is attracted towards the south pole. So, the rotation will be in the clockwise direction. So, the rotor will rotate in the clockwise direction like this. Similarly, PT3 is feeding W2. So, the field will be moving from this position to this position and then after some time the field will be moving to W1 to this position, and hence we have a continuous rotation which is in the clockwise direction. Now, this is a simple principle of a brushless DC motor. Now, this brushless DC motor is used for very inexpensive applications. For example, the fans in a computer power supply. All of us are familiar with the computers. In the computers, we need a fan and the fan is basically for the cooling purpose. Now, this is an example of a computer fan. You can see here that this is a computer fan, okay, and this is a brushless DC motor, because this fan is going to run for years together without getting damaged. So, if we go for a simple DC motor having brushes and commutators, we have frictional contact there, the contact will develop problem, and once the fan stops, the cooling will also stop. So, this fan is supposed to run in dusty environment without any problem, because it does not have any brush. Now, if we see the back side of this, we have the rating of the fan, and the rating shows that it is a 12 volt fan, approximately 0.14 ampere or 140 milliampere. So, roughly it is close to, let us say, 2 watt. So, it is basically a 2 watt fan which is used for computer power supply. Now, we can open up this fan and see the structure inside the fan. These are basically the connectors for connecting the DC power supply, which is plus 12 volt, because in computers we have DC power supply. And if we remove this inside region, we will see that the fan is the rotor. Here the rotor is basically surrounding the stator. So, these are the magnets. The magnets are placed inside this, they are buried here. So, we have south pole, north pole, south pole and north pole inside this, and this is free to rotate. We have a shaft here and the shaft can go into this and this can rotate freely. And if you remove this, this shows the structure of the stator. Now, we have seen that the stator in this case has concentric winding. You can see here that we have all these windings here, the copper windings are placed here, and here, for example, here we have 4 windings, 1, 2, 3 and 4, and these windings have to be excited depending upon the rotor position. The rotor is a magnet, this is a magnet, the magnets are arranged inside this, and this is the stator which is inside, and the rotor is free to rotate. So, the stator is excited, as you have seen that we have a photoencoder. Similarly, the rotor position is sensed and these windings are excited, maybe W1, W2, W3 and W4. And since we have 4 winding, we must be having 4 transistors. Each winding is excited by a single transistor. So, in this case we are expecting that these windings should be connected to at least 1 transistor. And if you see very closely, there is a printed circuit board here which is attached to this stator. It is stationary and connected to the external power supply. So, this is the printed circuit board, and in the printed circuit board there are very less components. You can see there is a single transistor structure here, and this has got 4 legs. These 4 legs could be for the 4 windings. Since we have 4 windings, this basically is a switch, is a power switch, and this will be switching the current to all these 4 windings. Since we have the DC power supply, the DC power supply is given here, so we have a switch, and then the rotor position is sensed here by Hall effect sensors. The rotor position can be sensed by an optical encoder. This can also be sensed by Hall effect sensors, because Hall effect sensors are the sensors which can detect the field position or the position of the flux lines. So, here the Hall sensors are mounted in this case, and Hall sensors along with the stator, mounted on the stator, senses the position of the magnets in the rotor, and accordingly the windings are switched on and off. When the windings are switched here, the field is produced in the stator, and when the field is produced in the stator, there is a torque production, and as the rotor rotates, the field goes on shifting, and hence there is a continuous rotation. So, this is a very inexpensive motor, but this is an example of a brushless DC motor. We do not have any brush. You can see here this structure does not have any brush. So, the disadvantages associated with brush and commutators are done away with. So, this is an example of a low cost brushless DC motors as we are just discussing, and in this case the rotor and the magnet positions are detected using Hall effect sensors. Now, if we come back to our discussion here, as the rotor rotates, the stator field goes on shifting. So, as a result we have a drawback, and the drawback is the torque pulsation. Now, if we see the expression for the torque is equal to K psi 1 into psi 2 into sine of the angle between them. So, we can say sine of gamma. So, psi 1 could be the stator flux, psi 2 could be the rotor flux, and gamma is the angle between psi 1 and psi 2. Now, in this case you can see that when a winding of the stator is switched on, the angle is approximately 120. So, in fact, gamma in this case varies from 0 to 120. All right. So, we have the expression for the torque, and gamma is not constant. We are not having any constant angle. In each revolution there are 3 switchings, because we are having 3 transistors, and the torque is proportional to sine gamma, and gamma continuously changes from 0 degree to 120 degree, and hence the torque varies as follows. So, if we see the plot of the torque, in this case as the time progresses, we can see that torque will change in the following fashion. It is varying as a sine wave, but varying like this. So, this is basically the torque, and torque is equal to k prime sine gamma. We can say this is equal to k prime sine of gamma, and gamma is not constant, gamma is in fact changing, and as the gamma changes, the torque is going to change. Now, what is the effect of that? Although we have average torque, we can say that we do have average torque here, and hence the rotor rotates, but nevertheless the torque pulsates. That is torque pulsation. The torque pulsation may not be dangerous in a small motor like this, a fan drive, but this could be unacceptable for high performance application like traction or an automobile applications, and hence this class of motors are used for low cost applications like fan applications, where the torque ripples or the torque pulsation can be tolerated. Now, we will go one step ahead. Now, here we have a structure like this. We are exciting this from a single DC supply, and the current in every winding is in one direction. We also call this to be a unipolar drive. Unipolar drive means the current in every winding is in one direction, and one winding is excited for 120 degree, and it is only in one direction. So, sometimes if you have 3 windings and only one winding is excited, the motor is not fully utilized. Say for example, if you have a structure in which we have the windings and we excite only one winding. So, we only pass current through only one winding. This is the number of turns here N, and these windings phase B and C. If we say A, B and C, phase B and phase C are not excited. So, if phase B and phase C are not excited, the MMF in this case is N into I. What we obtain here is the MMF. The MMF is in this direction, and that is equal to N into I. So, this is a unipolar drive where only one winding is excited at a time, and this results in low torque production. On the other hand, if we excite all 3 windings and have facility so that each winding can carry bidirectional current, both positive and negative, we could have higher torque production. Say if we connect this and connect this in star like this and pass current to this winding also, we can have say I by 2 here and I by 2 here, and this is the same number of turns N and N. So, in this case we have Ni produced by phase A, Ni by 2 produced by phase B, and Ni by 2 produced by phase C. So, we have excited 3 windings right now, and each winding, one winding is carrying I current, other winding is carrying I by 2 and I by 2, and hence the total MMF in this case can be calculated here. The MMF being vector, this is 60 degree, this also 60 degree. So, we can say that the total MMF is equal to Ni plus Ni by 2 into cos of 60, and since we have 2 other phases multiplied by 2. Now, cos 60 is half. So, if we see here that cos 60 and cos 60, so we have one force in this case. So, Ni plus Ni by 4 into 2, and that is 3 Ni by 2. So, what we see here is that when we excite all 3 windings, we get an MMF that is 3 by 2 times of Ni compared to when we are exciting a single winding. So, it is always beneficial to have a brushless DC motor where we can excite all 3 windings simultaneously, and that is possible in a bipolar drive. So, we will see the structure of a bipolar drive. So, in a bipolar drive, we are talking about a 3-phase bipolar drive, 3-phase bipolar drive. What we have here is the following. We have an inverter. An inverter has got the transistors, 6 transistors here. And these are the antiparallel diodes. So, we have the 3 terminals which are coming out, in this case are connected to phase A, phase B and phase C of the motor. This is the DC voltage, and the motor has got 3 windings, phase A, phase B and phase C. This is A phase, this is B phase and this is C phase. So, this ABC terminal of the windings are connected to ABC terminals of the inverter. So, here we operate this inverter in 180 degree mode. In this case, if the current enters into one winding I, this comes out of the other 2 windings I by 2 and I by 2. So, in this case we ultimately have an MMF which is 3 by 2 times N into I, which is higher than unipolar drive. So, we will be discussing in the next lecture about a bipolar drive and associated control structure with a bipolar drive, and how to have same the clockwise rotation and also anti-clockwise rotation.